So while there are rules that enable us to painlessly compute derivatives, some calculus teachers like their students to be able to use the limit definitions to compute some of the simpler derivatives. So we'll be going over a couple examples of that in this video. Recall that the derivative of a function f of x is denoted f prime of x, and it's defined as the limit as h approaches 0, the function evaluated at x plus h minus the function evaluated at x, all over h. And again, the h is within the 1 over h is within the limit. So it's the limit as h approaches 0 of the following: the function evaluated at x plus h minus the function evaluated at x over h. As you might expect, computation of derivatives using the limit definition involves all the algebraic tricks we use to compute limits. In particular, it involves tricks that allowed us to get around the indeterminate forms. And the most common indeterminate form is 0 over 0. So the first function we're going to be finding the derivative of is x cubed plus x. We'll be using this limit definition here to compute the derivative of this function. So if we evaluate this function at x plus h, we'll get x plus h, the quantity cubed, plus x plus h. And if we subtract from that the function evaluated at x, so that would just be x cubed plus x, and divide by h, we get this entire expression here. So what would happen if we plugged 0 for h into this expression? Well, this would just become x cubed. This would just become x. We'd have x cubed plus x minus x cubed plus x. Well, those would cancel, and we'd get 0 in the numerator and 0 in the denominator. So we get 0 over 0 if we just plugged in 0 for h. So to get around this 0 over 0 indeterminate form, we're going to have to do some algebra. So I went ahead and pulled out the 1 over h here and expanded this expression. So we'd get x cubed plus 3x squared h plus 3xh squared plus h cubed, and then plus x plus h, and then minus the quantity x cubed plus h. Right off the bat, we can see that this x cubed here will cancel with this x cubed here, and these x terms will cancel as well. We have a plus x here and a minus x here. So what are we left with? We're left with 3x squared h plus 3xh squared plus h cubed plus h. And now let's go ahead and divide by h, divide through by h. So, and we'll have the limit as h approaches 0 of 3x squared plus 3x, or sorry, 3x squared plus 3xh plus h squared plus 1. And now that we've done all the necessary expansion and cancellation, we're actually ready to go ahead and take the limit. So in taking the limit, we'll have to ask ourselves, what do each of these terms do as h approaches 0? Well, this 3x squared term is really independent of h, and so is this 1 term. As h approaches 0, that has no bearing on 1. But 3xh is going to go to 0 as h goes to 0. And h squared is going to go to 0 as h goes to 0. So we're just left with 3x squared plus 1. Now we're going to work a slightly harder example. We're interested in computing the derivative of the square root of 1 plus x squared. So recall that the derivative of a function f of x is f prime of x, and it's the limit as h approaches 0 of the function evaluated at x plus h minus the function evaluated at x all over h. And in this particular case, f of x plus h is the square root of 1 plus the quantity x plus h squared, everything under that square root. And the function evaluated at x is just the function itself, so minus 1 plus minus the square root of 1 plus x squared, and then all of that's divided by h. And if you plug in 0 for h here, you're going to get, this is just going to become square root of 1 plus x squared. You'll subtract the square root of 1 plus x squared from that, which will just be the square root of 1 plus x squared minus the square root of 1 plus x squared. So that'll be 0 in the numerator, and we'll have 0 in the denominator. You'll get another indeterminate form. And if you look at this difference of radicals here, you may not know how to proceed. But recall that in the past, when we've been confronted with either a sum or difference of radicals, what we did was we multiplied and divided by the conjugate. And that almost always helped us, and that's exactly what we're going to do here. So I've made a little note here that the conjugate of the square root of a plus the square root of b is the square root of a minus the square root of b, and vice versa. So in this case, we have expression of the form the square root of a minus the square root of b, so its conjugate will be the square root of a plus the square root of b. So we're going to both multiply and divide by that conjugate, because remember, if we multiply and divide by the same number, that's equivalent to multiplying by 1, so we're not really changing the value of the quantity here. So the conjugate of this expression is the square root of 1 plus x plus h, the quantity squared, plus the square root of 1 plus x squared. So we're going to multiply and divide by that quantity. So when we multiply and divide by the conjugate, in the numerator we'll just have the square of this expression minus the square of this expression. So the square of this expression is 1 plus x plus h, the quantity squared. The square of this expression is just 1 plus x squared. And in the denominator we'll have h times the conjugate itself here. Oops, I should have closed this parenthesis here. So I went ahead and expanded this expression here to x squared plus 2xh plus h squared. And what you'll notice is that you'll have a 1 and a minus 1 here, so these will cancel. And you have an plus x squared expression and a minus x squared expression, so those will also cancel. And what you'll be left with is the limit as h approaches 0 of 2xh plus h squared over h times, and I'll just say times the conjugate here. So you can see now that there are some cancellations in order. If we factored out an h here, we'd have the limit as h approaches 0 of h times 2x plus h over h times the conjugate. So this cancels here, and all we're left with is the limit as h approaches 0 of 2x plus h over the conjugate. If we write down the conjugate here and go ahead and take the limit as h approaches 0, this numerator will go to 2x. And this denominator, well, this first expression will go to 1 plus, or the square root of 1 plus x squared. You'll have another plus the square root of 1 plus x squared. So the denominator will go to 2 times the square root of 1 plus x squared. So numerator goes to 2x, the denominator goes to 2 times the square root of 1 plus x squared. 2's cancel here, and you're left with x over the square root of 1 plus x squared. Hopefully you can see from these two examples, using the limit definition to compute a derivative just amounts to doing a lot of algebra to circumvent the 0 over 0 indeterminate form. And really, as long as you're good with the algebra tricks from the limits, you should not have too much of a problem computing derivatives using the limit definitions, although the algebra will get very, very tedious very, very quickly.